simple probability and compound probability. If you remember compound probability, here's the key word for compound probability: and. I'm going to roll a 3 and then a 4. I'm going to pull a king of hearts and then I'm going to pull an ace of hearts. The key word for mutually exclusive and inclusive events is going to be the word or. I'm going to roll a 2 or I'm going to roll a 3. It's all in the same roll. I'm just going to do one of those rolls. So the key word to mutually exclusive and inclusive is the word or. Now let's talk about this. So mutually exclusive and inclusive events. These are events that cannot occur at the same time are called mutually exclusive. If two events are not mutually exclusive, then they're called inclusive. So let's start with mutually exclusive events. Here's the symbol for mutually exclusive. Note that we have a regular kind of right side up U. In math, that stands for or. Yesterday, it was upside down. That stood for and. So today, we're talking about or statements. Now, to be mutually exclusive, these are events that cannot happen at the same time. Can you, on one die, roll a 2 and a 3? And you can't have one of those cockeyed ones because you didn't roll anything then. So no, they're considered mutually exclusive. You can either roll a 2 or you can roll a 3. If you need to calculate the probability of rolling a 2 or a 3, note you are going to add your probabilities together. You are increasing your likelihood. When you multiply with probabilities, you actually decrease your probability. So when I do my probability of pulling a king of hearts, that's 1 out of 52. And then I'm going to pull an ace of hearts, that's 1 over 52. When you multiply them, you have a much less likely chance of pulling both those cards. For rolling a die, we're going to do the probability of rolling a 2 plus the probability of rolling a 3, so that will increase our probability. So the big thing is, or leads to adding. Or leads to adding. All right, so that was our probability exclusive. Probability of inclusive. So inclusive are events that kind of double up. And before I get to this, let's talk about what I mean by an example of that. So we have a deck of cards. And I ask Sahej to pull out a king or a heart. Now, why this is considered inclusive is because there's one card that satisfies both of those conditions. And that is the king of hearts. So in that regards, you have to add the probability of pulling a king plus the probability of pulling a heart. But I want to note, we counted the king of hearts twice. We counted the king of hearts here, and I counted the king of hearts here. So this says subtract the overlap. Realize that you counted it twice and subtract it away. So once again, if I ask the hedge to pull out a king or a heart, she will come up with the probability of pulling a king, which is 4 out of 52. The probability of pulling out a heart, which is 13 out of 52. But then you have to subtract one card because you have one card that has an overlap. So this will be subtract the overlap. Big thing here is or means add. And ask yourself, is there an overlap? Is there something that occurs at the same time? A king of heart occurs in both categories. Okay, let's do some examples. A card is drawn from a standard deck of playing cards. Find the probability of drawing a king or a queen. Now, your job in these is, first of all, go, okay, it's an or statement, so we are adding. We are adding, which means it's going to either be mutually exclusive or inclusive. Would this be an example of an inclusive or an exclusive event? Looking at that definition, would these be inclusive or exclusive? Yeah, they would be exclusive. There's no such thing as a king-queen. You're either a king or a queen. These are mutually exclusive. There is no overlap. There is no king of queens. Well, it's a show, but so it's exclusive because either it's a king. What did I put it? Yeah, either it's a king or queen. There is no overlap. So that means the probability of pulling a king or, do it the right way, or queen is going to equal the probability of pulling a king plus the probability of pulling a queen. Note, for mutually exclusive and inclusive, it's happening at the same time. So we don't have to worry about replacement. We don't have to worry about are we keeping it, because this is the same pull. What's the probability in one pull to get a king or a queen? What's the probability of pulling a king out of a deck of cards? How many kings are there in a deck of cards?
4.
There's 4 of them. So we'll have 4. How many cards are in a standard playing deck? 52. And then we're going to add, same thing for the queens. There's 4 queens out of 52. Now remember, to add fractions, you must have a common denominator. We already have that. And so we're going to have 8 over 52. We can simplify that. Yeah, 4 goes into both things. So we're going to have, wait, did I say 2 or 4? Oh, 4 does, yep. So we're going to have 2 over 13. Or means add, or means you have to decide is it exclusive or inclusive. Our next one, find the probability of drawing a king or a spade. I kind of went over this example. What is that, inclusive or exclusive? Is that inclusive or exclusive, and why? Yeah. Yep, inclusive because there's an overlap. We can pull the king of spades. So this is inclusive. And it's inclusive because of the king of spades. It falls into both categories. All right, since it's inclusive, we're going to go, okay, probability of pulling a king or a spade. I wonder if I can draw a spade. Does that look like a spade? Kind of. Thank you. Thank you for the support. A king or a spade is going to equal the probability of pulling a king plus the probability of pulling a spade. I guess I'll just put spade. It took me too long to draw it. But we are going to subtract the overlap because I'm counting the king in this one. I'm counting the king in this one. You can't pull the king twice. You can't pull the king of spades twice. It's only one card in a deck. So we're going to subtract the probability of pulling out the overlap, and that's the king of spades. Okay, probability of pulling a king, that is 4 out of 52. The probability of pulling a spade, any one of our suits has 13 cards. It is a quarter of your deck. So pulling a spade would be 13 out of 52. And then we're going to subtract, there's only one card that has an overlap, and that's our king of spades, so we're going to subtract 1 out of 52. Well, adding all that together, we had 4 plus 13 equals 17 minus 1 is going to give me 16 over 52. So that's going to reduce down to 4 over 13 again. Yeah, Rose.
Why couldn't you just do 4 over 52 plus 12 over 52?
You could.
Oh, okay.
That's what we're doing. This is just a better setup for when we have more complicated problems, when we're just like, okay, well, how much stuff is overlapping? But you just did the subtraction in your head. You're just like, oh, there's an overlap. I'm not going to count the king of spades twice. That's all we're doing.
Okay.
However you want to do that, more power to you. Just make sure you understand the logic behind it, that we are subtracting that overlap card. And don't subtract it twice, because now it's gone. Okay, Problem number 2. In a group of students, 60% are commuters, 50% are female, and 30% are female commuters. Find the probability that a randomly selected student is either female or means add, that we're going to be adding, which means we have to decide, is it exclusive or inclusive? In this problem, is this an exclusive problem or is this inclusive? Yeah.
Inclusive.
Why?
Because of female commuters.
Because of the female commuters. So it's inclusive because there is that overlap of female plus commuter. A female commuter falls into that 60% and also falls into that 50% category. All right, so we're trying to figure out what's the probability of pulling out a random selected student, either female or commuter. So what we need is we need the probability that the randomly selected person is female. Plus, what's the probability that they are commuter? Now, we counted too many. We counted too many because one of these females might also be a commuter. We need to get rid of that overlap. So in this case, we're going to subtract away the probability that it's a female commuter. And they listed the probabilities up there. We don't have to turn them into fractions. If you want to, you can. But we can just stick with, probability of someone being a female, well, that's 50%. So we can put 50% right here. Probability that that person's a commuter, that's 60%. Well, right there, if you forgot to subtract something, you should be like, I have a 110% chance of pulling. That doesn't make any sense. Probability only goes up to 100%. So that'd be your sign that we should have subtracted something, and we need to subtract the overlap, which are female commuters, which is that minus 30%. So that's going to equal, we have an 80% chance of that randomly selected person being a female or a commuter. You could turn that into fraction if you want to, 8 over 10. But I'm going to stick with 80%. Example 3. Example 3 is a more difficult problem that you have to really think about it. Because depending on what I ask, I can give you this exact same problem and change a little bit of it, and I can alter it from being inclusive to exclusive or from exclusive to inclusive. So you have to really think about what the question is asking. So it says, when a pair of dice is rolled, find the probability of observing a sum of 12, or, remember, or means add, so I have to decide if it's exclusive or inclusive. At least one die shows a 2. So our job is to decide this could be exclusive and it could be inclusive just depending on these two numbers. So what you need to do is you need to come up with all the different ways that there are to add up to 12 and then see if 2's involved in any of them. So let's look at the different ways to add to 12. Well, to add 12, we could do 6 plus 6. What other way can we add to 12? That's the only way. Does that involve a 2? So is there any overlap? There is no overlap. So this would be exclusive. There are no ways to add to 12 that involve a 2. So they do not share any link. So because they're exclusive, we just have to come up with the probability of our sum being 12 or the probability of it having a 2. Well, since it's exclusive, we just have to do the probability that our sum is going to be 12 plus the probability that we have a 2 showing. Well, the probability that our sum is 12 is pretty easy. It's just 1 out of 36. We'd have 1 out of 36. Showing a 2 is a little more complicated, because that means we need to have at least 1 2. But if I have all these drawn out, it's pretty easy because we have all of these. Make sure you don't double count 2 and 2. Make sure you don't double count 2 and 2 when you're actually physically counting these. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 different ways to show a 2. So that'd be 11 out of 36, which would equal our 12 over 36 equals 1 over 3. I want us all to stop here for a second. Think of a way that I could change this number that would make this an inclusive event. What could I change this number to? So I'm adding two things together. Right now, if I add them to 12, they aren't inclusive. What could I change this 12 to that would make this a mutually inclusive? What would make this mutually inclusive? Rose? 3 through 8. So if I need to add to 3, yep, we'd have a 1 and a 2, and we'd have a 1 and a 2. Basically, like you said, any number between 3 through 8, because 8 would involve 6 and 2. Anything bigger, and we can't add to it. So this could be mutually inclusive if I just change this to any number between 3 and 8. Does anyone have questions on that? Why did Rose say 3 and 8? Are we all okay with that? Okay, so be careful on problems like this. Changing a number makes it completely different. Did I show that twice? Yeah. Okay, complement. This was the question from the homework today. That was the at least question. Our complement. When I brought up the fact that you have a 20% chance of failure, you can go, at least I got an 80% chance of success. Those are known as complements. They're opposites of your probability. One is success, one is failure, but they must add up to 100%. So a complement of event A are all outcomes that are not in the event, and we call it A prime. That's called A prime or A apostrophe. We call it A prime. So A prime stands for the opposite of what I'm looking for. So in the homework, that would be, we're looking for at least one red. The complement would be no reds. In some cases, finding the complement is easier to calculate. In fact, there are some cases where you have to find the complement first. There is no way to go directly into the actual answer you're looking for. So for example 4 says throw 2 dice. What is the probability that 2 die are different? What is the probability that 2 die are different? This is a very, I guess we could do it without doing the complement, but we're going to do this one with the complement. So what is the probability that 2 die are different? So the probability I'm looking for that 2 die are different but what we're going to do first is we're going to calculate the complement. So if the probability of the 2 die being different what would my complement be? So my probability is that 2 die are different. What's the complement of 2 die being different? What breaks that? Yeah. Getting pairs. So the probability of 2 die being different, the complement, what if they're not? What if they're both the same? That's the probability of both the same, or they're both pairs. So let's calculate the probability that both are the same. And we did that yesterday. Now, when I'm looking for both of them being the same, that's 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, right? There are really 6 possibles that work out of 36. The way I could show that through multiplication, if I didn't want to go through that whole thing, well, my first die doesn't matter. It's your second die that matters. So your first die can be any numbers you want it to be. That's 6 over 6. I just need to roll that first die. Now that first die turns out to be a 1. What's the probability of my next die being a 1? Yeah. 1 out of 6. Now remember, the 6 over 6 actually accounts for any roll. It could be a 2, a 3, a 4, a 5. That just means your second roll has to match that first roll. So that's going to equal 6 out of 36, which is just 1 out of 6. So really the only thing that matters is our opposite. Okay, so our complement is 1 out of 6. Now we're going to calculate our event. Remember, our event is our regular probability that is going to be 2 different. Two different numbers. I guess we put numbers. Well, to calculate that, we just need the opposite of 1 over 6. Well, that should end up being 5 over 6. It gives us that 100%. But when you calculate this, if we get to more complicated numbers, I'm just going to let you know that your probability is going to equal 1 minus your complement. So in this case, I'm going to make 1 my 6 over 6 minus your 1 over 6, which would equal 5 over 6. Most of the time, you don't need to show this calculation. You just got to be, okay, 1 out of 6 is my failure, so 5 out of 6 must be my success. I need those two things to add up to 100%. Just like if I say you fail 20% of the time, you're like, nope, I succeed 80% of the time. It adds up to that 100% or that 1. That is using our complement to find our event. So you find your complement first, you kind of flip it, and you get your actual event. All right, the next one says the letters of the alphabet are written on 26 cards. 2 cards are chosen at random without replacement. Okay, 2 cards are chosen at random without replacement. What is the probability that at least one of them is a consonant, including y? What is the probability that we have a consonant, including y? All right, so we have without replacement. So that means we have a compound event where the second series of it is affected by our first. So it is dependent. All right, we're going to calculate the complement first. And what's going to tell me to do the complement first is this word right here, at least. At least almost always says you're going to do the complement first. At least tells you the complement's going to be the easier way to go. So we're going to calculate the complement first. So we're going to do the probability of A prime. The probability of A prime, since it's our complement, is really just going to be the probability of both being vowels. At least one being a consonant. The opposite of that would be I get no consonants. I have both vowels. Does that make sense? So I'm looking for the probability of getting at least one consonant. The only way that breaks is if I get no consonants, which means I have both our vowels. So we're going to calculate that first. How many vowels do we have? A, E, I, O, U. Yeah. We got 5 of them. So what's the probability that my very first number is, or letter is a vowel? We'd have 5 over 26. Okay, now I have a vowel in my hand. I'm not replacing it. What's the probability that my next one is also a vowel? What is the probability that my next one is also a vowel? So I have 5 over 26. My first one's a vowel. What's my second one? Yeah. 4 over what?
4 over
25. Yeah. Because that pull affected both of them. Okay, so that's going to be our probability that we both have vowels. So that's going to be our 20 over our 650, which you can reduce to 2 over 65. Let's just do the eye test right now. What would my probability of this complement, what would the probability be of getting at least one consonant just using the eye test on kind of this consonant? We're not going to do any big math. What would I do to get that probability? Rose?
1 minus 2 over 65.
We do 1 minus 2 over 65. Or we might just do, 63 plus 2 would be my 65. So we should end up with 63 over 65. Like I said, a lot of times it's just easy to kind of picture what number this needs to be to make it equal. But we're going to actually do the whole math. So that means we're going to do our actual probability, which is probability A, which is at least one consonant. And that would be our 1 minus, and maybe I should move that over a little bit, put a little divide. Boom. Now we're doing our thing. That would be 1 minus our 2 over 65, which we should get out as 63 over 65. We're just looking for what would make that top when added equals 65. Well, those are pretty good odds. But that is called the complement. Do not forget about the complement. If you feel like you cannot do it, on that homework, when you got to that red one, it should have felt like I can't do this for some reason. This is why we didn't know what the complement was. So keep that in your back pocket. If you can't calculate something, see if you can calculate the complement of it. All right, the very last thing we're going to talk about is odds. Odds. If you ever heard anything about odds, you probably heard the phrase 6-to-1 odds or 10-to-2 odds. However, few people actually know what these numbers exactly mean, and even fewer know the context surrounding the odds affects what they mean. Definition of odds. If A is an event, then the odds in favor of A are defined as the ratio of probability of A to the probability of its complement. And the odds against A are defined as the ratio of the probability of the complement happening to the probability of the event you want happening. Too many happenings. All right, for example, what are the odds in favor and against of getting a sum of 5 when rolling a pair of dice? What are the odds against a sum of 5? I don't think I want to do both of these. Maybe I do. What are the odds in favor and against of getting a sum of 5 when rolling a pair of dice? Let's just get rid of that second. It's kind of a double question. That's why I was slightly confused. Get rid of that second part because I'm already asking for the sum kind of thing. So get rid of that second part. It's kind of not needed. Okay, what are the odds in favor and against of getting a sum of 5 when rolling a pair of dice? So we need to calculate both things. What's the probability of it happening? And what's the complement of that probability? I need both of those things to come up with our odds. So the probability of getting a sum. So let's go, that's my probability A. That is, what's the probability of getting a sum of 5 when rolling a pair of die? Well, a sum of 5 might mean that we want to turn a page to that whole list of die we have. So we know it's out of 36 because we're rolling 2 die. So either we turn to the other sheet or we can think in our head, How many different ways are there to add up to 5? What's one way I could take 2 die and it adds to 5? Yeah, man. 1 and 4. What's another way? 2 and 3. What's another way?
5 and 1. Oh wait, what are we doing?
We have 1 and 4. We have
2 and 3.
2 and 3. What's another way? 3 and 2. What's the last way? 4 and 1. So we have 4 different... Oh, don't do the homework yet. All right, so we have a 4 and 36 chance of getting a sum of 5. So either we think that way or we go back to that sheet and we look it up, which means we actually have a 1 and 9 chance. We also have to calculate the complement. That would be the probability of not a sum of 5. What would the probability of not getting a sum of 5 be? Carly? It'd be 8 over 9. All right, we're supposed to calculate what's the odds in favor and against. So odds in favor are basically our success first and our failure second. So the odds in favor let me write that a little more clearly over a little bit further. Let's just go favor. Are going to be, well, success first, that'd be 1 over 9, to 8 over 9. Against, we'll just flip those and go, okay, failure first, 8 over 9, to 1 over 9. In alphabet you'll see that 2 being replaced by colons. I'm not going to do this in class, but you'll see online or something like that, it'll have like colons here in place of that 2. We're just going to stick with 2 to not confuse people because this is just a small section. All right, that's odds in favor and odds against. Now, example 7 is going to go the opposite way. It says the odds of hitting a single number in a roulette are 37 to 1 against you. So against means this is my failures, this is my success. So we have 37 to 1. What is the probability of winning in percent? Okay, so we need to put this one in a percent. Now, the biggest mistake you're going to make on the test is, what's the probability of winning a percent? You're going to go 1 over 37, got it, I'm done. That is not true. It is not 1 over 37. Just remember, this is the probability of you failing. This is going with the probability that you win it. So we would not have a 1 in 37 chance. So this is how many times you fail. This is how many times you succeed. Now remember, in probability, it has to be basically how many times you succeed out of the total number of possible outcomes. There are 38 possible outcomes. You fail 37 times, but you succeed once. There are 38 possible outcomes. So our possible outcomes are going to be 38. So my probability, let's just go P of getting that number, P of getting our number is actually going to be, I have 1 success out of 38 possible, possible outcomes. Which if you plug in your calculator, so if it asks for percents, would come out to about 0.026, which would equal 2.6%. So the quiz on Monday. A bunch of you are going to do 1 divided by 37. Remember, this is your failures to success. So our total possible outcomes are actually 38.